I mean, so this textbook sometimes puts some important topic in the exercise so that you work on the exercise so you learn this thing. This is so-called Parseval theorem. I mean, the integration of the square of the function is related to summing over the square of the coefficient. The theorem is especially simple if you use a normalized basis, of a normal basis. But even if you are not using that, that's fine. The way he is asking 19.1.4 is using the, the cosine and sine series. So we could just work that out. What it is. This is 1.4, right? So we just go back to the the form of the series, which is 19.1 fx. Yes. Yeah. This constant term and all the and cosine term is n cosine n x. Right? Is n. Right. And all you need to do now is just to work out the integration. So integrating minus pi to pi. The domain of the or the period of that this function is different. So f squared. This is assumed to be real. I mean, but if it is not real, then you can use. I mean, you can use complex quantity, but assuming it's real, just assume if f is real, obviously all the a's of n and b's of n are real. Right? Just do the straightforward integration. That is pi to pi, and you have the square of this one, right? And to write the square is better write it in, instead of writing square, you write two series. So you have a sub 0, and this, and right, just one factor, and then you just copy the same thing for the other factor. But this time, obviously, you don't use the same n, you only use m. So it is back to m, b sub n. So this. Okay. Then obviously, this using sine and cosine, it's the unfortunate thing. You have different cases. Using the complex series is much easier to prove the theorem or write down the final form. But for sine and cosine, you just need to consider k by k. So you have the constant term times the constant term, right? And the constant term comes the constant term, and integrating over the x over this period obviously is the AC is over 2 square and then multiply the period. So that's easy. So equals to AC over 2 times 2 pi. And now you have the terms that So constant times the rest integration, or this times the constant, the same thing. Those will be zero, obviously, right? You see that? Because all these are periodic functions, and you just run of them, and they have all they're non-zero, they're non-constant or non-zero. So obviously you integrate over 2 pi, that those will be zero. So you don't need to consider this time now. A sub 0 times the rest, you don't need to consider. So it's this summation times this summation. And when you do the summation, so there are cost term, the n not equals to m, and n equals to m. So there's quite a lot of term. But now you probably can use the consideration that we talk about when we divide the formula for a sub n and b sub n. We cite those considerations, which you can show quite easily. Say, like you consider cosine. You have cosine nx, cosine mx, and they will be zero if n not equals m, and that you can show that by using those formulas. You know, multiplication of two trigonometric functions. We have formula like that, and convince ourselves that there will be a sum of two sinusoidal trigonometric function. In this case, it will be 2 cosine, and it will not be non-constant if n not equals to m. The only case is constant n equals to m. There will be a constant, and that case, so it will be a Kronecker delta n m. When n not equals to m, will be 0. When n equals to m, your cosine. This is for n larger or greater than 1. So if we ought to take the constant term consideration out. When n equals to m, your cosine square, and average over 1 period, you get 1/2 times the period. So that would be pi. Okay. And so now you take care of all this times that. You use this one. And similarly, the sine times sine, you also have that. This one, a sine. It's be the same. And all the cos term, again, using those product rule for trigonometric function, and convince yourself that it's all zero. Okay, this is n, both n and m. Okay, so is it you all can accept this one? You don't need me to show you. Is it okay? You know what I mean? Using those formulas. Remember those are supposedly you learned in the high school. Now you use those, then all these times this integrate, and you pick up only n equals to m and has a pi, and in that case you have a n. So everything has a pi plus sum over. So only when n equals to m, when they are the same, you get this one. So that will get rid of one summation and leave you one summation out. So you have 8n squared. And similarly, you have this times that, you have bn squared. And there's no correspondent. So a times b, all these will be zero because of that. And also this too. Okay? So this will be the form of the Parseval theorem. Just it's whatever the function you expand it in Fourier series, the square of this function integrate over the period is given by this form, or the square of the coefficient, and then I multiply by corresponding the corresponding factor get the proportion to the period. That for this a sub n, b sub n, this is pi, and for the zero term is actually 2 pi. So the Fourier series using sine and cosine has this kind of things. You need to be a little careful. The zero order term and the rest are not exactly the same. So that you just need to be a little careful. So using the complex series has an advantage as the math is slightly easier. But now the question asks you that if this is finite, if this is finite, it means that this series must be convergent, right? For this series of convergent, but one of the necessary condition, obviously, this number must be goes to zero. So is n squared is supposed to zero and goes to infinity, because those are all positive terms. Those are all positive terms, and they don't cancel each other. You add them up. If they are not going to zero, obviously this would diverge. So so that would be the requirement that the f square integration is finite. Okay, so that is pretty obvious, right? If it's not zero, if it actually turns to any constant or even growing up, then you sum over it to infinity, this must diverge. So in order for this f is to be convergent, then you must at least this is necessarily not necessarily sufficient for this to be convergent. So there could be stronger statement, but then at least an's the square of an and b sub n, they should go to zero. Okay, is that okay? All right. So that is so-called Parseval. I don't know whether the text has the name that writing down some Parseval or Parseval relation or whatever they call it.
It has it in problem 19.1. That's the equation.
Yeah. Right. Yeah. That's right. Why didn't I get the exact? Oh no. This is pi. This is square. So so it's 1/4. This is 1/2. So there's a 1/2 actually. Yeah, right. And divided by pi over the other side is yeah. Yeah, this is part B is Parseval identity. So